Start.
Equals 2, Teil 3, ja.
Boa tarde. Chegamos então à terceira e última aula do minicurso número 2, ministrado pelo professor Bernd Hofmann. Bitte, Professor Hofmann.
Yeah, dear colleagues, I have still some rest of the part 2 in my slides here. And yeah, I'm very sorry that so often I use, as examples in particular, Hilbert spaces. But Hilbert spaces are important Banach spaces. So this is not so hard. But yeah, if you understand Hilbert space theory, regularization, then you have a first idea for Banach state. But not so far. A couple of minutes, I will really come to the Banach space situation, which is not Hilbert space there. Some points have been mentioned on Tuesday. I will recall this for having the continuation in a smooth way. Yeah, we considered convergence rates for Tikhonov regularization, and the effect was that we could, in the classical Engel-Kuhnisch-Neubauer theory, published 1989, the first convergence rate results of Tikhonov regularization for nonlinear problems. We have seen there are 3 conditions. There is a source condition, there is a smallness condition, and there is a nonlinearity condition. And the problem is, if the source condition works, that means that you have a fine source condition and a fine smallness with it. Then the question is, what is necessary for the nonlinearity? And Engel and his colleagues have shown this rather simple. This is the simple condition which I had written here. If C3 is 2, which means we have Lipschitz continuity of a Fouché or Cathode derivative, then all works fine. What happens if the benchmark source condition doesn't hold in that way, or smallness is not to be achieved? Yeah, then we can use the method of approximate source conditions. I discussed it a little bit. Approximate source condition helps, but only if the nonlinearity condition is strong enough, which means you need something like condition, tangential cone condition, or index function of condition of tangential cone condition. So in Hilbert, classical Hilbert situation, classical Engel-Kuhnisch-Neubauer theory, you have a real gap there. If the benchmark source condition fails and tangential cone condition also fails, then you have nothing. You have no convergence rate results. In the very simple situation you have the so this is the problem, and I gave you this is example of very simple autoconvolution equation in the Hilbert situation L2, and yeah, we show that nearly nothing worked, and you cannot have something, and yeah, the question is, if nonlinearity condition only is the simple one, you cannot apply the approximate source technique. And so, yeah, the question is, you must try to solve benchmark source condition plus smallness condition. And yeah, there is a hope that this works. Otherwise, you have no rate. In the simple situation of autoconvolution in Hilbert, the simple situation you can have there. So, and here I've written a proposition. Apart from the rather trivial case that you take as reference element the exact solution, then you need not work further. In all other cases, to satisfy this, you need some additional conditions. You need, for example, such a relation. In some sense, you must be very good in your reference function, and moreover, you must, this reference element at the right end must be identical with the values of the exact solution at the right end. Much to do, and yes, you see, there is a very small chance to satisfy this here. This is only the question for the benchmark source condition. Yeah, and nice gag. If this reference element is 0, then you have x dagger and minus x dagger, and both are in the same distance to this reference element. So the minimum x bar minimum norm solution, here is this exactly the norm minimum is x and minus x star dagger have the same distance. And you cannot get a rate because the system does not know, go to left or go to right. So in that case, the solution have the same distance, and it is not possible that such things can be satisfied. So the simple situation you have.
Bernd, I have a quick question. You have that condition x bar 1 at 1 equals x dagger at 1. And why don't you have something similar at 0? Or is it just a choice you are making?
Yeah,
because you're integrating up to 1.
Yeah,
the
see, maybe I find it here in the first say. The classical situation here is so that I must go back a little bit. Situation is that you use this in that way, that the minimum norm needs, this is the best approximation to this x bar. And so if x bar is 0, then this is the minimum norm. And now for autoconvolution, x dagger and minus x dagger have the same distance to 0. And you have not a uniquely determined x bar minimum norm solution. And this ambiguity gives the problems at this point. So this is not a nice thing, but yeah, you cannot do something against. Last, before we really come to the Banach space situation, the problem which occurs here is that if you have a look at, let's say, at this is benchmark source condition. You have to satisfy in order to get it.
Okay. So
and now, but this smallness condition in this way is this. So if you look at this and say, okay, this V with this moment defines an operator, then finding x dagger here is nothing but the fixed point problem. You have a fixed point problem, and the operator has the property by this V equals 1, has the property that Banach's fixed point theorem occurs. And this theorem tells us, okay, there is exactly one solution, and therefore, in principle, there is only one solution, and you see there is a trivial solution in general here, and you cannot find reasonable solutions in that way as you do it here in that way. This only was a little bit a rest of yesterday, of Tuesday. So more important now, questions, okay, all the things doing by hand, benchmark source condition, nonlinearity condition, all by hand you do it. So is it possible to make it a little bit more modern, more smart here? And the idea of doing this is the following. We have another way of characterizing the solution smoothness. In this way, we call variation source condition. It's a way of variation inequalities in that way. If you see this, it's not nice. It's a little bit strange, but it's really helpful. And you see here, there is a difference of the penalty functionals, a variable and the solution point, and there is an index function of this norm difference here. And this E is nothing but an error measure. For example, in Hilbert space, you can think it's x minus x dagger norm squared, as we have always. And this beta is a technique which helps to bring situation into that setting which not directly come there. This beta is, or these things work, if this beta is any value greater than 0 and smaller than 1, if you have 1, then directly on the left-hand side, you have the error measure. I will give examples here. Another point is the question, what is this M? This M is a set where this variation inequality has to be satisfied. And in principle, M must contain all regularized solutions. Let's say if the delta, the noise level is smaller than some upper bound, small enough, in an interval from 0 to delta bars, let's say. So, and this variation inequality has to be satisfied only for such elements. And yeah, if M is the whole space, all is fine. Then you have no problems with this. For example, if M is the level set of this R of the solution, this is the R x dagger is here always the R minimizing solution, the smallest value. Yeah, if you have a little bit more than this, epsilon or C more, and you need this level sets here, and you can show for all level sets, then all is fine and all works. This is the simple situation you have here. I recall a situation, if you have this alpha choice, a priori or a posteriori, alpha goes to 0, but not too fast, then you get convergence, at least in a weak sense, if you have Kardec-Clay properties, also in a norm sense. And yeah, from the definition of the theorem of regularization, you also get that in addition to this weak convergence, also the R values converge, and also the F values converge in that way. This is rather helpful. This helps you to consider the things a little bit more. Now, some words, very small number only, about the parameter choice. You can choose the regularization parameter a priori, but a priori choice always a problem. You can choose the regularization parameter a posteriori if you have the noise level delta available. So one of the traditional form of doing this is, for example, Ramlau wrote a couple of papers there, is such a form of discrepancy principle. You have this delta, you take two values greater than 1, tau 1 and tau 2, such that, and you search for an alpha, I take it alpha star, such this is in an interval. But if linear problems occur, this is fine, you can have it. You can have it for linear problems equal tau delta, and it works, because the function of this discrepancy is growing non-linearly but continuous. But in nonlinear problems, this is not the case. You can have such things that if alpha starts with 0, then this function, this discrepancy function grows with alpha. And it may happen that at some points there's a jump, duality gap jump, and so just this delta or tau delta can be in this jump. And so you have no chance to get it. Therefore, I do not like this so much, and we use always the so-called sequential discrepancy principle, SDP here called. We make nearly the same, but a little bit more smart, I think. We start with a big value alpha, and such a geometrical sequence, Q, for example, a half, is often used. Yeah, and we say if the first time this tau delta value for the last step, the discrepancy is greater, and for the next step, the discrepancy is smaller, then we stop at this point. So then the gaps are not a problem. You jump over the gaps and have a good solution there. So in principle, it works well. one can show that alpha goes to 0 and delta to p divided by alpha goes to 0 with the exception of one case I call, or we called, exact penalisation veto. This exact penalisation veto is as follows. We say that this veto is satisfied if we, with the exception of singular cases, I do not discuss here, sorry, for an arbitrary alpha, for arbitrary regularization parameter, an error minimizing solution X dagger cannot be a minimizer of this. And here, please have a look. This is the exact right-hand side. If this minimum cannot be the same as the regularized solution, then the exact penalisation veto is satisfied. We have papers with a couple of colleagues, Peter Mattei and Stefan Anzengruber, where we discussed it over 20 pages, so a little bit more. And a little bit trivial said the only case is p equals 1. If you have in the discrepancy power p equals 1, then this veto can be failed. But otherwise, for p greater than 1, this veto is always attainable, and you can, with the exception of very extreme situation, you have it. So, and so you see, then it works, and you have at least such weak convergence situation. Now, and this is in this setting, it's a general Banach space setting. From my point of view, at the moment, one of the most important theorems I present here. We have discussed this and with Peter Mattei published in Inverse Problems, and it is the following. If we have this variation in source condition, you will ask the question, how to get it? I will answer this after. If we have this variation in source condition, and the M is such that all regularized solutions for sufficiently small delta satisfy this, and if p greater than 1, then such veto does satisfy. And first situation, alpha is selected by a priori parameter choice in the following way. Alpha is delta to the p divided by this phi. Phi is the phi function, is the function which occurs in the variational source conditions. I try to go back here to show this. This is the phi here in this form. And rather, without deeper explanation at this point, this phi function is nothing but the result function of the rate. If you have such a variation in source condition, you directly know the rate. You have this phi, and this phi is the rate function. So this is really nice, and this is the advantage, the disadvantage of this a priori case. You must know it here. You must know it. I will show then an example where I do not know it. By principle, you do not know it. But so then a priori parameter choice is, stupid. It does not help. But we have another. We have our sequential discrepancy principle here in this, and we take it and say, okay, alpha star then by sequential discrepancy principle, and for that situation, as for the a priori situation, we need not know this phi, and we have in the same way the following. The error function is always very general a non-negative function, non-negative distance function between regularized and exact solution. This is big O of phi of delta. You see, this is really the rate. If delta goes to 0, this is the rate. It's clear. It's not interesting for point by point, this X dagger, this X dagger. It's interesting for classes, formulating classes, source sets, let's say, with these properties. Moreover, we have the F is big O of delta, and also the absolute value of the R differences is big O of phi of delta. As a general theorem, I cannot make the proof here. It's about 4 or 5 lemmas, and goes over 7 or 8 pages. And so, but it's clear there are very different proofs for such theorem by different authors in the last 10 years. And a couple of colleagues told me, if I understand this, I should read this proof. It is a little bit long, but everybody understands it. Otherwise, the other proofs are also not so long, but very technical. But if anybody is interested in this, please read this paper for having the proof ideas, because they are very clear, not very short, but very clear here in this way. Now the question, I have presented this version source condition. It's a stupid mathematical expression, and is it realistic? And this in this small chapter, I want to show this. The first situation is the benchmark case, which means we have a range type source condition. Here in the Banach space now, a little bit new Banach space, you have not the situation that the operator F or A star in the linear case works such that it maps from Y to X, but in the Banach space, the adjoint works from Y star, from the dual space, to X star. And the element is a subgradient also in the X star. So this subgradient must be in the range of this. And yeah, and if you have it, this would be the simple case. You need not hear anything more than this. You can show it. Then this will imply our variation source condition. I have written it here. You see it. This is this left product. You can transform it. You can estimate it by Cauchy-Schwarz inequality. You can go to norms here. And now, little trick, you can add this R difference simply, and the result is nothing but here I have a Bregman distance. That means this E here is the Bregman distance between X and X dagger. And if you do so, you see, this is the right thing. So now, if this would be a linear problem, and this would be an A, then you are ready. You have the variation source condition. If not, then you need now some theory about nonlinearity things, and you can try to formulate the things more. In the special case of Hilbert again, you see this is in this form a little bit simpler, but in the same way. Here you have as a Bregman distance the norm square. You have this R difference, and you have this form, and you see benchmark source condition, Hilbert space, you get here this F prime, and yeah, if this is a linear one, you immediately have phi of t is t. You have a rate, big O of delta. Now you say diagonal of regularization, big O of delta, never heard. There is a saturation. You cannot have more than delta to 2/3, but please note, the error is the norm square. So you have not delta, you have in principle for the norm square root of delta. And so disadvantage of this method, overall, better is impossible. You do not can leave the concave index function. So you end at this point. And all the theory around between half and 2/3 is another thing. You must have additional tricks and so on. But here, all is nice. Alpha goes to 0. This quotient goes to 0. What happens if this penalisation veto fails? P equals 1. Then Osher and Burger have shown then it's enough to have the alpha small enough. It's not important how to, it must be small enough, then you get it. So in a paper with four authors with Andreas Neubauer in 2009, we constructed a situation where in the case that this penalisation veto fails, we even have the situation that you get the right rate, the optimal rate, but the alpha must be exactly one value which depends on the solution. So I did not believe that such things can occur. But if the penalisation veto fails, all can happen. Then you cannot see it. Such situations I will not consider here. Now, benchmark source condition, best possible rate, square root of delta for the norm, nothing but. What happens in other cases? For example, structure of nonlinearity is important. If you have such a form, which I discussed a little bit on Tuesday, and here is again an index function and strongly concave index function. Let's say tau to the power very small greater than 0. Then you see this sigma index function occurs here, and you can do the same thing, and you see the phi function for my rate is now characterized by this. This nonlinearity structure defines here the rate. Beta would be sigma of t is t, best rate. But if you haven't it, then you will have a worse rate in the same way. The alternative structural condition, which I have written here, in the Banach space situation attains this form. Here on the right-hand side, you have a constant multiplied by the Bregman distance. Such things were considered by Elena Resmerita or Ottmar Scherzer. And this is nothing but, I mentioned in autoconvolution case, but here in a general form. If you have this, you can also use this technique. And if you have no such kind of tangential cone condition, again, as we know from Hilbert space situation, you need additional smallness condition. This is near this. Then we additionally need the smallness condition, and only with this smallness condition you get the same thing. And in the optimal case that benchmark situation occurs, then you have again proportional to t, phi of delta is proportional to delta, or in the Hilbert space square root of delta for the norm. Now what happens if benchmark source condition is violated? We can again apply our method of approximate source conditions. Now again in the Banach, real Banach space situation, you see you take now all is in X star in the dual space. You take the smallest distance if the radius of the elements V are limited or bounded by R. And so you can characterize this again as a function. We have discussed this with Radu Botz in a paper in 2010. Non-increasing continuous and concave, and under normal conditions goes to 0 as R goes to infinity. And all is fine if the second adjoint of f prime is injective. This works in general in normal cases if the f prime is injective. This is only a technical condition, but now you need some point more. This Bregman must be bounded below by some exponent of the norm. And if you do this, for example, such things are fulfilled if you have this standard version of R in the Banach space with some Q big enough here and so, then you can make this in the same way, and you get also these things, and you see if you estimate it here, you have such a sum. R occurs here, and you can evaluate the R such that this is an equilibration between these things, and this equilibration helps that you get a Bregman distance in that way. And now you add these things I did, and you see you use Young's inequality with such a help auxiliary function, and you get such a not very nice but available function, and you see this is the function, and here I've written only for the linear case, such that for the B you get such a version inequality, and here this rate function comes from the distance function, from this auxiliary function, and from this Q, which is in the coercivity of the fragment. A little bit technical. There are papers which, yeah, if one reads it, I think it's not very complicated. Now, you have seen one word, this beta can be smaller than 1. In this approximate source condition things, you get not beta 1, but the smaller one between 0 and 1. This is the role of this beta. It helps still a bit if other things do not help. Now, my favorite section, really Banach space theory, L1 regularization. The idea was there is a fast literature on sparsity in L1 regularization. In principle, sparsity, Ottmar and his group has written many papers about this. If you have sparsity, it means you consider an LP space and you say, okay, this is an infinite long vector and only a finite number of elements are non-zero. So nobody knows how many, nobody knows where they are, but in such case you can show in principle this situation is a well-posedness situation. You have a well-posedness and you can work with this well-posedness, but now our discussion was as follows. In most cases, in practice, it is not true that you only have a finite number of non-zeros. You have an infinite number of non-zeros with some rest. They are epsilon-like values, but they exist. And so our assumption came in the following. We make L1 regularization. X is L1. Pay attention that this is that has a pre-dual space C0, which is a separable pre-dual space. Weak star topology works here in that way. We use Tikhonov regularization in that form. And now the question is as follows. If we know the solution is not necessarily sparse, but at least L1, that means there can be infinite number of remaining rest components. We cannot avoid such rest components in that way. And what happens? Is it possible to get a rate? And so this was a discussion with Martin Burger 3 years ago. And Martin told me, no, I do not know any paper which gives an answer there. And we tried it with all things. We tried it with source conditions. It was shown there is no source condition in the range type form. We tried it with approximate source condition. There is no approximate source condition in that form. But the last point is to get it by the variation source condition. And Jens Fleming was very helpful. He had very good ideas in technical handling of such things. And we really got some result under some not very hard assumptions. We assume the solution is in L1, not in L0. We have such a weak convergence. This is not very strong. This is a condition in principle which shows the problem is ill-posed. Otherwise, it would not make sense. If the problem is well-posed, you need not handle this too much. And this is a very technical condition, or seems so that it's a very technical condition. The EK, that's a long vector, which is at the case point 1, otherwise 0, must belong to the range of the f prime of the solution applied to some element fk. So this seems to be very technical, very restricting, but we could show in a paper with Ronny Ramlau and Stefan Ansengruber that this situation mostly occurs, and in particular for the linear operator, it is the standard way if the operator is injective. So it's not really a hard condition. And now it's a nice thing. Under such a nonlinearity condition, you see, we again assume such type of tangential cone condition with a sigma function which is of index form. Then we can show there is such a variation in inequality. You see, now our error function E is an error in L1. And yeah, the standard form, and this phi very enthusiastic is how is phi? How is phi here? Is it available? And really, in particular, Jens had good ideas here, and we could show this phi has this nice form. If you look at it, it's a little bit strange, but one can explain it good. The first part is the remaining components, which are sparsity plus rest. This is the rest of the sparsity. What happens with the remaining, with the rest components, if k goes to infinity? The other type is, here is our sigma function from the nonlinearity, and here is such a sum, the first n elements of this condition which occurs here in the characterization of this, and yeah, and it could be shown this is really an index function, it is really concave, and nobody can compute it. So it's clear, it's a function which occurs from this technical things here, and so it's clear, a priori parameter choice of the alpha you can forget about, but sequential discrepancy principle works very well, and you can work with this, and I will give you some situations one can understand. The whole situation is as follows. You say the rest component, let's say all components from the n plus first until infinity, the rest components have a decay like n to the minus mu. It's a realistic situation. And the sum of these characteristic elements in this source have a growth like n to plus nu. Moreover, we assume that this sigma, the nonlinearity situation, has such a growth like t of kappa. So we have three, mu, nu, and kappa. And this kappa is between 0 and 1. And nu and mu are greater than 0. And one can show then there, from this theory, general, we get such a rate. And you see here this rate is mu times kappa divided by mu plus nu. If nu goes to infinity, you see here, if this goes to infinity, this was smaller and smaller. If mu goes to 0, then this was also smaller and smaller. In all other cases, if mu is big enough, and nu is big enough, then you can get the converse situation. And so, in principle, by choosing this SDP, you get a clear rate, and you see, okay, if you know all the exponents, you have a good rate for this situation automatically by using the SDP. This is a nice thing, and we have no idea if anything other ways can lead to such a result here in this way. So there are a couple of papers coming from this. This is a paper with Martin Burger, Jens Fleming in 2013 in inverse problems, and about 4 or 5 papers came after that in order to improve some details here. Last point here, Peter Mattei asked me, okay, what happened if the remaining components are, such as one expects, extremely small, they decay exponentially. So then the rate should be nearly the same rate as we had when we really had sparsity with a finite element, finite non-zeros. And really we can do it. Exponential decay of these and other things in the same way. We have here the simple situation that we assume we have a real tangential cone condition with a t, not a t to the power. And then you see the error is a logarithmic factor multiplied by delta. And this logarithmic factor is characterized by these things. You have only very, very, very small deviation from the delta rate. And the delta rate, as you see, is just the rate which you get if the solution is 0, if you have only a finite number of components. It's completely the same where the components are, how many components occur, but how many and where, of course, occurs here in the constant of this. This constant can explode if the situation. So it's only the rate question in that way. But you see, if the decay of the remaining components is exponentially, you have nearly this same. Only this logarithmic factor is the perturbing factor in this way. Antonio, can we change to the third part? The third part is small, so please. I will not.
With respect to the parameters of the problem?
Yeah, the discrepancy is in principle the term in the misfit. So you say, if you use discrepancy principle, then you say the misfit must be of order as you define it. So this is the idea. You know, this discrepancy, or this misfit term, grows with alpha. If you have the misfit term, and you apply the misfit term to the regularized solution, let's say f of x alpha delta minus y delta norm, then this grows with the regularization parameter, and you take some level where this growing function crosses some constant. This is the idea here. So in principle, it's a use of the misfit in this specific form. Third is, you have the, it's not so much. And, sorry, enough abstract Banach space. We mostly come again back to the Hilbert space where one can explain things a little bit better. I want to speak here about one other thing which is very closely related to this, conditional stability. And there is a close connection between regularization, rates, conditional stability, and rates, and I will try to explain it. I will try to explain it in particular, considering the factor. Let's say we go to Hilbert space. We go to p equals 2, and so we have the situation alpha must go to 0, delta squared divided by alpha must go to 0. So this is the standard form. All I had up to now occurred there. And now we will see this is not an intrinsic thing. That is only for this specific situation. You will see in this second part here that for conditional stability, it is necessary that delta squared divided by alpha does not go to 0 and does not go to infinity. You have two constants, C1 and C2, and between these constants, the quotient must stay. Then all works fine. In the third point, this is a very challenging thing, and I would be happy. I would be very happy if I could find friends for this. I call it over-smoothing regularization or over-regularization. What does it mean? Up to now, we always had a situation that R of x dagger, penalty functional applied to the exact solution, has a finite value. We did never think about it. We thought it's clear, must be, otherwise it makes no sense. But you can have the following situation. The solution is a function in L2 and not in H1. For example, Heaviside. So you know it's not in H1. But you do not know that it's Heaviside. You know only, okay, this maybe if you have a penalty which is very smooth, you can get good rates. So smoother and smoother, better and better. But if there is a conflict in that way that you take R as a norm square of H1, and the solution is not H1, no solution is H1, then all the theory, breaks down here, it collapses in some sense. Nevertheless, we thought there must be rates. Why? There is a paper by Frank Natterer from 1984, where he showed that for linear problems in Hilbert spaces, all works fine. And for these situations, he can get rates. And just for this over-regularization, the rates are completely fine, continuous, all works nice. There is no result away from this. There is no results for nonlinearity anyway. There is no results, for example, if you take small L1 as a penalty and this small L1 is too much for the solution. Such things, no results. So we tried, we made a very small step, like on the moon, only one step, nothing more, and I will want to present it. But the interesting thing is the quotient of delta squared divided by alpha then must go to infinity. You can only be successful if this quotient goes to infinity. Otherwise, it doesn't work. So you have three situations: quotient to 0, quotient in constants, quotient to infinity. And this is the goal of my third part I want to show a little bit here. If I have still time, some words about Lavrentiev regularization, which is much simpler, but only applies for accredited function in the linear case or monotone functions, monotone operators in the nonlinear case. Only my star and 2 star, you know, and definitions for ill-posedness, linear, nonlinear, I do not speak too much about. Yeah, in principle, Tikhonov regularization and conditional stability, you know, Tikhonov regularization. I go again back to Hilbert space in order to can explain it better. You have this well-known situation, I discussed it, and here I make this symbol here. This quotient has to go to 0. This is the symbol for giving this situation. All we did up to now is successful if this condition works. Now you can show the main point is this, what I call minimizing property. The regularized solution, Tikhonov functional, has the property that the regularized solution is left and the exact solution is right, and you have this inequality, and you have some implications. For example, one implication is that between the reference element and the regularized solution, you have this distance. Between the F element and you have this distance. You can show a couple of things, and yeah, now one can work with it. Yeah, one can use this variational source condition as we have done it. Here I have only repeated this. For this specific situation, our theorem again, Hilbert space situation, I had it in a Banach space. Now we again formulated specific in the Hilbert space situation. And you see again the situation is of this type. You can show that in both cases, a priori, a posteriori, you get this situation. And now the situation, what is different with respect to conditional stability? The first part we know all, and we can skip here. But conditional stability, and if you have a look at this, yeah, it looks very, very similar. Very similar like variational source condition. What is missing, the difference of the penalties is missing here. This kind, here only for simplicity written in the Hilbert space situation, but very general, such conditional stability estimates are often presented, discussed in PDE theory. For example, Klebanov and such names. You find a couple of results. In my paper with Masahiro Yamamoto in 2010, Masahiro presented at the end over 15 pages or so proof of such a conditional stability for a PDE problem. And yeah, such problems really exist. And what is the difficulty here? The difficulty is they exist and do not only hold on some specific set. For example, in PDEs, if some additional condition is satisfied, boundary condition or norm condition or such things, I say there is a set Q. And only in the set Q it is satisfied, and set Q is not available, is not you cannot handle with this Q. You have such a nice thing. If you have this, you say, then by my definition, you must say this is well posed. But this is not always well posed. It is only well posed on this set. So, and if you do not Q, you cannot use it directly. You must find a solution for coming to Q. If you see this, you can say, if you have such form of stability, such form of local well-posedness, where you need not do something more, but if you do not know Q, then Tikhonov regularization helps very good to handle these things, and the value of the Tikhonov regularization is only to find this Q, to come with approximate solution in this Q, and then you can apply the well-posedness, the local well-posedness here in this way. This is the idea, the rough idea. First nice paper was presented in inverse problems by Cheng and Yamamoto in 2000. This is the seminal paper of this, and I will give only some points here. Yeah, under this condition, I wrote it only for the Hilbert space situation, because one can see under this situation you can use a priori parameter choice in that way that you say the alpha of delta should have a constant multiplied by delta squared as a low bound, and this upper bound also a constant multiplied. And you see, if you divide this by delta squared by alpha, then there is an upper bound, a lower bound. There is nothing to 0, nothing to infinity. And yeah, you can do it, for example, if you say, oh, I take alpha star as 5 times delta squared, and it should work. So what happens there? You have such nice properties. And here I use these properties with such a sign to show this is not to 0, this is constant in that way. If we use this minimizing property, we can again reformulate it, and at the end you can follow these lines very simply. You get a difference norm square in that form, yeah, and you see this difference norm square is, yeah, fixed value is bounded by a fixed value. And now if you know our radius, and here please see I use here a Q, which is a ball around our solution. If the radius of this ball, where you have conditional stability, is with respect to that value big enough, then we can, with this x alpha delta, come into that Q area. And if you are in this Q area, domain intersected with the Q area, in that way, yeah, you can apply directly the conditional stability, the conditional stability estimate, as you see here. And what you do is nothing but this. You apply this directly with triangle inequality. You use the estimates we had, and you arrive at this norm square error is constant multiplied by this phi function. And this phi function here is nothing but the phi function, which defines here the conditional stability. Often a power type function t to nu with nu small value 0.2 or such thing are often showable. So my joke, using regularization under conditional stability is like putting into the hole while playing golf. So you do nothing, but you must put this in, and if it's in the hole, all is fine. You can work with this. So this is my point of view of this conditional stability.
So the practice point, you should compute somehow this R, so you can find the region and you can play the golf.
No, in general, you must have an area of conditional stability which is large enough. No? Yeah. It must not be such a ball. It can have another. In general, you will get it. In particular, if you have a convergence, you get a convergence, then you know for sufficiently a small delta, you are in an area which at least weak convergence, and then you can expect that you come into.
But this R is not, you cannot compute it, right?
No, you cannot. No. But in general, it's not a ball. It can have a simply different character. But if you have a solution, and if the regularized solution converge at least in the weak sense, then it makes no problem from my point of view. It makes problems in the case of oversmoothing regularization we have here. Oversmoothing regularization, I show it in a rather simple way, and this rather simple way is our very small step in order to come to another result after the very, very old paper by Frank Natterer from the 1980s. And our idea was as follows: can we stay in Hilbert scales but go to nonlinear equations, and can we get convergence rates there? And up to now, we haven't found any result which helped there. Why? The minimizing property would have this form here. And the minimizing property, the right-hand side is such that there is some R, and we know R of the solution is infinity. So this is nothing. It's not helpful. You cannot do anything with this. So we tried to find the following. We started with a discrepancy principle in that way. Simply, it must exist. Duality gaps can be against. So this is an assumption, technical assumption. Will the number of problems where the simple, this is the simple form of discrepancy, where the simple discrepancy principle fails, is, I think, smaller than 1 promille. But one can show it, that the worst case is bad. And so, we have forgotten this at this moment here. And you see, here the situation is different. And if you have a look at the paper by Natterer, he only discussed linear problems, star problems, one-star problems. One can see he used a priori parameter choice. And if you study this a priori parameter choice in Natterer's paper, nobody mentioned this up to now, then you see, really, this must go to infinity here. I've never seen that anybody mentioned this. So we must live with this, but it's not a problem. So our setting is as follows. We use a linear unbounded operator B, self-adjoint, which characterize a Hilbert scale in the well-known form. As you know, this is the scale variable tau. This is the characterizing operator. And so you get such a Hilbert scale situation, and Hilbert scale situation as also Natterer did for linear problems. And our D is now this intersection here, and we take Hilbert scale situations, but we write it in a standard Tikhonov form. Now for the nonlinear problems, and now here, this B occurs. You see, you have here this differential operator applied to that x minus x bar difference as a norm square here. So the question is, when is the solution, or the exact solution minus a reference element, let's say, you can omit it here, then you have only this. When is this not available in the sense of a classical form? If this value, if you use x equals x dagger, is infinity. So how can you proceed this? You can proceed this in the following way. If you say, my solution belongs to the domain, but my solution does not belong to the domain of this differential operator. But you are in this Hilbert scale, but it works. Then we know that the power p between 0 and 1 gives finite values. That means in the interval p 0 until not 1, but 1 minus epsilon. We have finite, but then it jumps to infinity, and the question is, okay, yeah, what happens in such a way? One needs some nonlinearity conditions. For example, such a form, also used by Nadra in that way. It's a technical condition and characterizes, let's say, the degree of ill-posedness in some way, with some positive value A here. This is in this literature, it's a standard technique here. We have it for the nonlinear situation. And under this, I will not show the details. It's very technical. You need auxiliary solutions. Auxiliary solution in the following sense. You know your exact solution is not in the domain of B, but in any surroundings, very small balls, you have elements with all smoothness. And so you take an auxiliary element very near in order to do this, but it's a rather technical thing. You need interpolation inequality, Young's inequality, such things for evaluating this. And the result is really, for that situation, for all P between 0 and 1, we assume for this P, the penalty is exact, finite, but for P equals 1 is infinity, then we get such a rate. And this is just the same rate as we had in the linear case by Nadra's paper. It works in the same way, but here with a discrepancy principle and with nonlinear problems. And unfortunately, one cannot follow the quotient effect here, but one can only see the lower bound of this quotient. This lower bound of this is anyway, but the upper bound is infinity. So I assume that always this quotient must go to infinity, but for the discrepancy principle, in contrast to a priori, we cannot show this. A couple of minutes I still have. Again, overview. You have this quotient goes to 0 for standard situation, finite penalty, Hilbert space situation of Tikhonov regularization. You have a constant between C below and C above for conditional stability. And in the oversmoothing case, you have a thing going to infinity. This is 3 situations which occur, which are real situation of Tikhonov regularization and surroundings here. And yeah, I hadn't seen this up to now, so there I wanted to show you that it's a phenomenon. Simply, one can explain this in such a simple way as I did, but it may be interest to understand it a little bit more and a little bit better than. Last point, Lavrentiev regularization. Sorry?
And you try to forget the new space in regularization with a parameter alpha. So in this case, you have a problem. Eventually, your operator the solution can go out. So conditional stability is basically.
And if you have conditional stability, you must have some kind of injectivity. Otherwise, it does not work. If you have Tikhonov regularization, you can have a non-trivial null space, but convergence rates, or convergence at all, I think, are only possible if you have minimum norm solution or X bar minimum norm solution. Only if the solution is orthogonal in linear, orthogonal to the null space. So you cannot come to a null space element in an exact way. Of course, but then you have the same thing with respect to that penalty. If the penalty, if under all solutions the penalty minimizer is unique, then you can come to this element. So, and then in such case, injectivity is only a problem which may occur or must not occur, need not occur. But for the classical form, if you have norm, if you have the norm squared or so, then you cannot come to some element which is not minimum norm solution. You have no chance. Tikhonov regularization always goes, in linear case, always goes to the application of the more Penrose inverse to the exact right-hand side. And this is always orthogonal to the null space there.
What means this is related to the height of the cave?
Yeah, we can discuss it. Okay. Let's go to the last points here. Lavrentiev regularization, very short, only for overview. Unfortunately, Lavrentiev regularization only works if you have a monotone operator. But if you have it for linear case, they are often called accretive operators. If you have it, then you need not minimize such a complicated functional as in Tikhonov, but you can do it in a simpler way, that you say you have the value and you add some alpha times, for example, the solution, or again with such reference element, and in principle you have now only to solve a linear or nonlinear operator equation. But very important, you must have monotone operators here in that point. So it's much easier computational from analytic point of view. It's much easier, and if you have monotonicity, then yeah, you will prefer it. Lavrentiev did this in 1962 or so. He wrote a nice book there, small book, and yeah, he showed it works. So it's clear, if you have Tikhonov regularization and you say AX equals Y and you multiply from the left-hand side by A star, then you have such a situation that A star A is a monotone accretive operator. You do, in principle, Tikhonov regularization in linear case is nothing but Lavrentiev applied to A star times this. So in principle, it's not a completely different thing. The technical things, I will skip most of these things. I assume that I have a monotone operator which is defined on the whole space. There was a long discussion last year about the question, can I use Lavrentiev regularization if the domain is restricted? There are some papers which are not exact. Maybe they are really wrong, but yeah, I do not discuss this here. I assume this, and for many such problems you have, where you apply Lavrentiev regularization, really this is a good assumption, because I feel, this is only a feeling, I feel that monotone operators and linear operators are very near. Most monotone operators are not far from linear operators, and so to assume that the domain is the whole space is anyway a good property. It's not, it's a realistic property. Technical assumptions I will not discuss too much here in this way. There is a concept of strong monotonicity in that way. You see, you have here the norm square in this form. I am in real, separable real Hilbert space here in order to avoid too technical things. You see, and this seems to be nothing but some kind of ill-posedness in that way. So this implies coercivity, and together with, you can apply the so-called Browder-Minty theorem, and yeah, you have all fine properties, surjective, bijective, all this, and so the inverse has this property. You see, that's very fine. You have well-posed situation in that form, and what is one of the backgrounds here? If you have a problem of the first kind for this, and you make Lavrentiev regularization, so in principle you get an operator which is strongly monotone then, and so yeah, Lavrentiev regularization is a tool to make the problem strongly monotone, and yeah, it works only if this strong monotonicity is it works only if you have a basic operator which is monotone, but by Laurentiev technique you get it strong monotone. So this motivates this a little bit. Barbara Kaltenbacher gave me a nice example, a nice simple example. I like simple examples in that way. I say, okay, she wanted to recover this Q, and inside there is a function which perturbs this. Otherwise, you could say, you take this U and make derivatives here, but you have here such a xi function, and this xi function Lipschitz continuous differential monotone increasing, and then one can formulate this. This is monotone, hemi-continuous, and one can work with this. One can show many things with this very nice, trivial but nice example where it works, where one can show a couple of things. I call an operator strongly monotone in a local sense if this works only in a ball, and locally uniformly monotone if we have here a function which is an index function. You see this is much more general in this form. But here this is local. So in principle you have the same effect like in conditional stability. You have such things only in the local way. And yeah, this local uniformity or local strong monotonicity works only in such a ball, and you need approximate solutions which come to the ball. One proposition, we formulate, seems to be rather trivial, but we formulated with Radu Botz in a paper in the last year. Let local uniform monotonicity hold with such an index function. And this index function should have the form that this is t times and also an index function. Then we have conditional stability estimates of this form, which means if you have such a local uniform monotonicity, you get a conditional stability estimate from the last round we had here. And in the same way, in a special case that this theta is proportional to d squared, we even have the strong monotonicity also again as a conditional stability estimate, and here see really again with Q such a ball. Radu has given me such a nice one-dimensional example in order to discuss this a little bit. You have a function in R1. It is -1 from minus infinity to the point -1. Then it has the character of a power function until 0. At 0, again the power function in a rotation symmetric way. And at 1, it is constant until infinity. Nice properties. We have local ill-posedness. Always if this local ill-posedness in the definition of my first lecture, if x dagger is minus infinity until in this interval until -1, or 1 or greater, you have local ill-posedness. There is a constant, it's clear, it's local ill-posed. At x dagger 0, we have local well-posedness for all exponents kappa. And due to the local monotonicity condition we have here, we have such a conditional stability estimate you see here. And if you look at the kappas, it's rather nice. If kappa equals 1, we have phi of t is t, the situation, which is nice. If kappa is greater than 1, then you get here a Hölder rate with an exponent between 0 and 1. But nice, if kappa is between 0 and 1, you get here a superlinear convergence. Such things also occur in that way. You have convergence, one-dimensional, which is is better than the simple convergence of a conditional problem, which is well-posed here. Now, our interesting problem was as follows. We discussed, when I was in Klagenfurt, I discussed with Elena Rismarita and Barbara Kaltenbacher the question, okay, so we have together, we discussed since 2006 the questions of variation in source conditions, can we find this only for Tikhonov regularization? Can we find such variation in source condition also for Lavrentiev regularization? And how can they show? And our preliminary result is as follows. If they have such a form, they can help. One can use Young inequality in such a very general form. All know with an index function f, you have here the inverse. You can formulate this Young inequality in that way. And this helps to handle such forms. You see the differences we had here, an index function of the norm difference. Now we have an index function of this inner product. And this inner product is greater or equal to 0 based on the monotonicity of the operator. So this is an index function of a value which is non-negative, and one can work with it. And now the most terrible theorem, which I have in my slides at all, the result is not nice, but it's helpful a little bit. You can find the error by such a characterization. You see here delta squared by alpha squared. This is typical for the Lavrentiev situation. And here the remaining term is rather strange. One can introduce this psi, this capital psi function. Let f be such an index function we have here, such that its antiderivative satisfies such a condition, and G has this property. Then we can formulate G divided by alpha, very technical, but it makes sense. If alpha is a priori chosen in that way, you get the classical form. Now in Lavrentiev form, not a square, but only a first power here. And the result is there is, based on the variation in source condition for Lavrentiev, we get such a rate result. And if phi is square root of delta, psi is proportional to t, we get such a rate, big O of delta over 1 over 3, if alpha is chosen as delta 2 over 3. And this is certainly not the optimal rate. With the variation in source condition in Tikhonov, we also did not get the best rate. We did not get the rate 2 over 3 in Hilbert space. We only got the rate 1 over 2. And here we get only 1 over 3 and not 1 over 2, which is here the best rate. So variation in source condition is a tool, limited, but often helpful. Logarithmic type can be verified here in that way. And you see from a logarithmic assumption, you get a logarithmic rate. And in the Hölder type, from a Hölder type assumption, you get a Hölder rate. Again, not optimal, but in that way. Last remarks, 2 minutes. Variation in source condition are very helpful. For linear problems, yeah, they are one tool, yeah, in the family of many other tools. But for nonlinear problems, variation in source conditions are a tool which often cannot be replaced by other tools, because in a variational source condition, let's consider particularly the Tikhonov situation, variational source condition, you have such a tool, left error, then the difference of the penalties, then index function of the f-norm difference. This kind includes all about the smoothness of the solution and much about the character of nonlinearity. So in this kind of variation in source condition for nonlinear problems, the character of the nonlinearity is included in it. If you have it, you need not think about the character of nonlinearity at all. You need to have it, but if you have it, then all is fine. So this is a real advantage. And for example, think about this L1 problem. If you have it, if you can construct it by other mathematical techniques, then you need not do this way as we had here with tangential cone condition, construction, degree of nonlinearity, all these things which are very complicated to show in practice. So, from my point of view, nonlinear problems are the real application of variational source condition. And only for these problems, the variational source condition will remain in the mathematical literature for the next 20 years anyway. For linear problems, yeah, it's one method of many. Thank you for your attention. This is the end of my small series of talks here.
Thank you, Professor Hofmann. So, are there any questions or remarks? So, I have one. How hard is it to verify these conditions, these assumptions for the
variational source condition.
Variational source conditions, yes.
Yeah.
Are there any important problems which you are aware?
I've shown you if you have other conditions, you can make conclusions to that. The L1 situation is the small L1 situation. You have nothing, but you have properties how to handle L1 norms at all. You can construct. If you see the proofs, you can construct from the theory of L1. There are some nice properties. You count in L1. You count anyway, and so this specific type leads to that formulation of the. You see this phi function as a sum of the remainders plus the sum weighted sum is very constructed, but you have it only from the intrinsic structure of the L1 norm there. Some lemmas and so. I hope that one can do it for many other problems. There are nice papers from the colleagues from Göttingen in the last 3 years. And they showed really for many also nonlinear problems, very specific nonlinear problems from different types, for example, identification in PDE. So that variation source conditions exist and which form this phi has. So please have a look at the papers of Frank Werner, Thorsten Hohage, and a couple of further colleagues. One of them, Frank Werner, will be here, and I'm very sure that he will discuss this a little bit. Okay. But it's very technical, and yeah, it is not seen by reading 2 or 3 pages. So, but I was very astonished that they could show this. They could verify the variation source condition for these complicated situations. So, but yeah, they are specialists in this field. Yeah, we did it from here. We did it from a very abstract point of view. They did it from a very concrete PDE point of view.
Any other questions or remarks? Please, Uri.
I was going to ask do you know of any work of this sort where people look at LP with P less than 1? I know that people have looked at P less than 1 in the context of trying to have more sparseness.
Yeah. In all my I have it. in all my slides here, I always had convex penalties, and if you go below, you get non-convex. A couple of papers exist for the non-convex case, but yeah, they need specific tools. They need tools where nonlinearity transformation are used, and so the first I know is from Sarza, from English group, but the theory for this is a little bit different. So all the things also Bregman, and so you cannot use because you haven't a convex functional, so you cannot define in such a simple way Bregman. Markus Grasmeyer wrote a couple of papers in this, and he did it with other technique. For me, a little bit technical. So, but if you go away from this abstract theory and you go to the practical setting, then it's true. If you have P, which gets from 1 smaller and smaller, you get more and more power on sparsity. So in principle, if you have really, if you know that you have sparsity, you can do it. The best would be to do it with L0. So, but then you have to minimize this. This is very complicated, I think. So we did it with the Chinese colleagues from Shanghai. But I'm not a specialist how to find regularized solutions if the penalty is L0. I think you need some Monte Carlo methods for or other things there. But you are completely right. If I have a discretization, then please take P smaller. For example, there are some very famous Chinese papers that P equals a half is the very best. This guy got a prize there. but it's a finite dimensional thing. It does not include in the theory at all. Thank you.
Okay, any other question? If not, let's thank Professor Hofmann again for the nice course. Thank you very much.
I thank for the patience or in the late time in the day, always 3 times.